Okay, so picture this scenario for a second.
Mm-hmm.
You're out on the deck of a destroyer, let's say middle of the Pacific.
Right.
The water is calm, sun's out, everything seems fine. Then the radar just screams.
The moment you never want.
It's picked up a sea-skimming missile, and it's not miles away. It's just breached the horizon. It's traveling at, what, Mach 2, Mach 3?
At least, yeah.
You do the math in your head and you realize you don't have minutes. You have seconds, maybe 5.
Maybe less. That's the nightmare scenario. That's the moment where every other layer, the jets, the long-range interceptors, the jamming, it's all failed.
The threat is through the gate.
And it is coming right for the hull.
And that is exactly where we're parking ourselves today. We are looking at the absolute last line of defense.
The goalkeeper.
Exactly. The system that wakes up when everything else is missed. We're talking about the Close-In Weapon System, or CIWS.
But it's a goalkeeper that has to stop a supersonic baseball without even blinking.
We've got a really fascinating report here from the Naval Sea Systems Command, NAVSEA. It's dated September 24th, 2025. And the goal for this deep dive is, well, it's to understand the philosophy behind a machine built to take over when human reflexes are just too slow.
That is the absolute key. It's about the shift from man in the loop to, in some cases, man out of the loop. Because when a threat is moving that fast, the human brain is just the bottleneck.
So let's start with the basics. We know it's for point defense, but what are we actually defending against in, today's world?
Primarily, you're looking at anti-ship cruise missiles, ASCMs. And the threat has just changed so drastically.
How so?
It used to be subsonic missiles flying pretty straight. Now you've got supersonic sea skimmers that do terminal maneuvers.
They zigzag right before they hit you.
Exactly, to throw off your aim. Plus, you have newer threats like swarms of drones or loitering munitions.
You have a small target moving incredibly fast, and it's actively trying to dodge you.
And you have to hit it. The NAVSEA report highlights this critical idea, the automated responses that exceed human reaction times.
Right.
Think about the ODO loop. Observe, orient, decide, act. A human sees a blip, they wonder, is that a bird or a missile?
Asks for permission to fire.
By the time they get to act, the ship is already hit. It's terrifying, but it's just the physics of the problem.
We have to trust the code because our neurons can't fire fast enough.
You don't have time for a committee meeting. You need a system that detects, tracks, and engages on its own.
The report breaks them down into 3 types: gun-based, missile-based, and then hybrid systems.
Right.
Before we get to the hardware, I want to ask about the kill mechanism, because shooting a missile with a gun seems incredibly difficult.
Well, you're looking for what's called a hard kill. You aren't just trying to poke a hole in it.
Okay.
With the gun systems, you're throwing a wall of heavy metal tungsten, usually at the warhead or the control surface.
So you either shred its wings so it crashes, or you
hit the warhead, and it detonates safely away from the ship.
Safely being a very relative term here.
Better than inside the hull. But yes, it's kinetic energy. You're essentially throwing a very fast rock at a bullet.
Let's talk about that rock thrower then. The Icon. If you've seen a Navy ship, you've seen that white dome that looks like R2-D2.
The Phalanx. The Mark 15 Phalanx. It is probably the most recognizable piece of naval hardware out there.
So let's pop the hood. It's more than just a Gatling gun, right? The report specifies the Mark 61 Vulcan 20mm gun.
It is, but the secret sauce isn't the gun itself. It's the mount and the fire control. It's what they call closed-loop spotting.
Okay, explain that. Closed-loop spotting.
So most radars, they just track the target. The Phalanx tracks the target and its own bullets.
No way.
It has a search radar to find the threat and a track radar to lock on. But as it fires, the radar actually watches the stream of rounds. It sees where they are relative to the target and corrects the aim.
In real time.
In real time. It's like watching a stream of water from a hose and walking it onto a target, but you're doing it at 4,500 rounds per minute.
So it's constantly self-correcting. It doesn't just calculate a lead and hope for the best.
Precisely. Because wind, ship movement, all of that changes the bullet's path. The radar sees the reality of where the bullets are going, not just the math.
The Navy Sea report had these photos that I thought were really interesting. One was the U.S. Coast Guard cutter James in the South Atlantic.
Right, doing a gun shoot with the Brazilian Navy.
My first thought was, why does a Coast Guard cutter have a Phalanx? Aren't they mostly doing, like, drug busts and search and rescue?
They are, but the line between law enforcement and naval combat is getting very blurry.
Yep.
Cutters are deployed in contested waters now. Think the South China Sea. If they get into a hot situation, they need that high-end self-defense.
And I guess it's good against other things, too, not just missiles.
Oh, absolutely. It's great against what they call asymmetric threats, fast attack craft, speedboats packed with explosives, drones.
So it can aim down.
Yep. It has a surface mode where it can depress that gun and turn a small boat into driftwood in seconds. That's a vital capability for them.
There's another photo, this one from the Arabian Sea, the USS Ronald Reagan. The caption mentioned strategic choke points.
Yeah, that phrase does a lot of work. Strategic choke points means places like the Strait of Hormuz.
Narrow passages of water.
Very narrow. So if you're a carrier strike group going through there, you are vulnerable. The land is close. A missile from a truck on the shore has a very short flight time.
So the reaction window just shrinks even more.
It goes from comfortable to claustrophobic. In the open ocean, a threat might be 200 miles away. In a choke point, it might be 10 miles or 5.
And that's where Phalanx is non-negotiable.
It's the insurance policy for when geography is working against you.
Now, the report brings up that the Phalanx was originally designed as a standalone system.
A bolt-on capability, yeah.
Which sounds good for retrofitting, but doesn't that create issues? If it's standalone, is it even talking to the rest of the ship?
Well, that's the tension. Originally, you wanted it standalone because integrating systems is a nightmare. You just wanted a box you could weld to the deck, plug into power, and say, protect this corner.
It had its own brain.
Its own radar, its own computer. It didn't need to ask for permission. But you're right, that is changing.
And the hardware is evolving, too. The Navy realized the gun has limits.
Range, specifically. A 20-millimeter bullet just loses energy really fast.
So how do you get more range?
You get the CRAM, the Sea Rolling Airframe Missile.
And this is just a brilliant piece of engineering.
It really is. They looked at the Phalanx and said, we love the sensors, we love the tracking system, we just want more reach. So they ripped the Gatling gun off and bolted on an 11-round missile launcher.
Using the same base, the same R2-D2 mount.
Almost identical footprint. Same power, same cooling. You can practically swap them out, but instead of throwing bullets 1.5 miles, you're throwing a missile 5 or 6 miles, maybe more.
And these rolling airframe missiles, the Rams, they're smart, right?
Oh, they are very smart. They have passive radio frequency seekers, so they home in on the enemy missile's own radar. And they have infrared for terminal guidance. It's fire and forget.
So the CRAM just gives you a bigger buffer. But the report mentions other adaptations that surprised me. It moved on to land. CRAM.
Counter-rocket, artillery, and mortar. Yeah? Anyone who served at a big forward operating base in Iraq or Afghanistan, they know the sound of this thing.
The Centurion, they call it.
Right, it's a phalanx on a trailer.
And it's used for stopping mortar shells.
Exactly. The radar tracks the incoming shell, predicts the impact point, and if it's going to hit something important, the gun just shreds it in midair. It's the same tech, just a different target profile.
And then looking the other way, into the future, the report mentions lasers.
High-energy lasers. This has been the holy grail for decades, and we're finally seeing them get fielded on these mounts.
What's the advantage of a laser?
Magazine depth.
You don't run out of ammo?
As long as your ship has fuel to make electricity, you have shots. A Phalanx runs out of bullets in, 20 seconds? A CRAM has 11 missiles. If you get attacked by a swarm of 50 drones, you have a math problem.
A laser solves that math problem.
Costs about $1 a shot, and you never have to reload.
But what about bad weather? I've always heard lasers struggle with that. The report mentions environmental immunity.
That is the big physics hurdle. Fog, rain, smoke, they all scatter the beam. It's a real issue. That's why you'll likely see a mix of systems for the foreseeable future. Lasers for the clear days, missiles for long range, and the gun for that last-ditch defense.
Let's pivot to the brains of the whole thing, the integration. The report talks a lot about Aegis.
Aegis is, it's everything. It's the ship's command and control system. It takes data from the huge SPY radars, from sonar, from other ships, and it fuses it all into one single picture of the battle space.
There's a quote in here from Nicholas Franzo, the Aegis program director. He lists the Aegis cornerstones. Fast reaction time, high firepower, environmental immunity, continuous availability, and complete coverage.
Those are basically the commandments of modern naval defense.
Let's pick one. Continuous availability. To me, that just sounds like it works when you turn it on. But it's more than that, isn't it?
It's so much more. It's about mean time between failures. It's redundancy. If you're deployed in a war zone for 6 months, the system cannot go down for a software update. It has to be running 24/7 in salt spray, in high heat. That's the difference between a prototype and a real weapon.
And complete coverage.
That's geometry. A ship has a superstructure, towers, antennas. You can't put a gun where it might shoot your own bridge, so you need multiple mounts, and the software has to know where all the blind zones are. Aegis coordinates that handoff.
So if a target flies from the port side to the starboard side,
The system has to handle that transition seamlessly without ever losing the track.
the report mentions the Naval Surface Warfare Center at Dahlgren. They seem to be the ones who make all this work.
Dahlgren is legendary. They are the systems integration experts, and the tool they use, this caught my eye, is called orchestrated simulation through modeling.
That sounds like corporate speak, but I'm guessing it's critical. Why simulate so much? Why not just go out and shoot more stuff?
Cost, for one, and complexity. To test this for real, you'd need to fire a multi-million-dollar target drone in a jamming environment and risk an actual collision. You'd get one data point.
Whereas in the model,
You can run that scenario 10,000 times in an afternoon. You can tweak the code. You can simulate an enemy jamming signal you haven't even seen in the wild yet.
so it's a digital twin of the entire combat system.
Exactly. The goal, as the report says, is to effectively communicate and coordinate. You don't want the Phalanx trying to shoot a target that a big standard missile is already on its way to intercept.
Right, that's wasted ammo.
And confused sensors. Dahlgren writes the logic that says, okay, big missile has this one. Phalanx, you stand down. Wait, big missile missed. Phalanx, you are weapons free. That all has to happen in microseconds.
It's like the machines are negotiating with each other about who takes the shot.
They are, and they're doing it based on probability of kill. P-Day, the system calculates, I have a 90% chance of hitting this with a missile, but only a 40% chance with the gun right now. And it makes the call.
So bringing it all together, we have the Phalanx, the CRAM, lasers coming online, all of it tied into Aegis. Naval calls this the standard for point defense.
It is the baseline. If you're a high-value U.S. Navy asset, you have this kind of layered defense.
The report uses a phrase, sustained combat at sea. That's a heavy phrase.
It is. It means we're not just planning to shoot down one missile. We're planning to stay in the fight while being shot at, potentially by dozens of them.
It's just incredible engineering.
Yeah.
But I have to ask, we are putting an immense amount of trust in these algorithms.
Where?
And you said it yourself earlier, man out of the loop. If the system gets it wrong, if it engages a friendly plane or failed to engage a real threat, there's no human hand on a switch that's fast enough to matter.
That is the inherent risk of automated warfare. We've crossed a threshold where the speed of the weapon dictates the speed of the defense. If the missile flies at Mach 5, you cannot have a human in the decision loop.
You just die.
You just die. So to survive, we cede control to the machine. We have to trust the testing. We have to trust the simulation.
It feels like a paradox. To be safe, we have to make ourselves helpless observers of our own defense system.
In the terminal phase of an engagement, yes. The sailor loads the ammo, maintains the system, sets the rules of engagement, but for those last 5 seconds, the machine is the captain.
That's a sobering thought to leave on. The next time you see that RTDT unit on a ship, remember it's not just a robot. It's the thing standing between the crew and the abyss, and it's thinking faster than any of them.
It is the final line.
Thanks for diving in with us. We'll see you on the next one.
Stay safe out there.